So you're staring down a calculus problem. You've got this whole toolbox full of rules, product, chain, quotient, but which one do you actually use? Which one is the right weapon for this specific job? It's a super common moment of confusion, and today we're going to build a simple system so you'll know exactly which one to pick every single time.
I mean, if you've ever felt like this Reddit user, you are not alone. You've hit one of the most common walls in calculus. It feels like the rules are all fighting each other. But the truth is, they're designed for very different situations. The real secret isn't about memorizing more stuff. It's about learning to spot the hidden structure of the problem in front of you.
Okay, so let's start with the most straightforward case. What happens when you see two distinct, separate functions that are just being multiplied together? Well, this situation calls for a very specific tool from our toolbox.
And that tool is the product rule. Now take a look at the formula on the screen. It's a pretty specific little dance, right? You differentiate the first part while leaving the second one alone, and then you just add the reverse of that.
Now listen, it is so tempting to just differentiate each piece and then multiply them. But that is the #1 mistake people make. Think about it. X cubed times x squared is x to the 5th, right? And the derivative of that is 5x to the 4th. Simple. But if you differentiate them separately first, you get 3x squared times 2x, which is 6x cubed. See? A totally different answer. This is exactly why you have to follow the specific recipe of the product rule.
All right, on to our next scenario. What if the functions aren't just sitting side by side? What if they're actually inside one another? Kind of like a set of Russian nesting dolls.
This is where the chain rule jumps in. You've got an outer function and an inner one. The rule is actually pretty simple. You deal with the outside first, leaving the inside alone, and then you multiply by the derivative of what's on the inside. It's all about working your way from the outside in.
Okay, this is the main event. We've got the product rule for multiplication and the chain rule for nesting. They seem really different, but out in the wild, these problems can look deceptively similar. So the real question is, how do we tell them apart every single time, without just guessing?
Well, the answer is a super simple test you can run that just cuts right through all the confusion. And you know what? It works almost every single time.
Let's break down what I call the stand-alone function test. First, you look at the two main parts of your problem. Then, you literally cover up one part with your thumb. And you ask yourself, can the part I still see exist as its own function? Then you swap. Now, here's the key. If both parts can survive on their own, you've got yourself a product. If only one of them or neither of them can survive, you're looking at a nested function. And that means it's time for the chain rule.
All right, let's try it out with y equals x squared times sine of x. First, cover up sine of x. What's left? X squared. Yep, that's a perfectly good function. Now let's cover up x squared. What's left is sine of x, also a valid function. Since both pieces survived our little test, it is crystal clear we need the product rule here.
Okay, now check this one out. Y equals cosine of e to the x. Let's cover up the e to the x. What are you left with? Just cos. That's not a function, is it? It needs an input. Okay, so now let's cover up cos. We have e to the x. That's a function. See? Since only one piece survived the test, it tells us that one function is nested inside the other. This is a job for the chain rule.
Okay, one more, just to really lock it in. E equals x squared times the natural log of x. You cover up ln of x, you're left with x squared. You cover up x squared, you're left with ln of x. Both are perfectly fine standalone functions. It's a product. This simple test just reveals the underlying structure of the problem every time.
All right, so there's one more major rule we got to talk about, the quotient rule. This is for when one function is divided by another. But here's the thing. I want you to think of this less as a totally new rule you have to memorize and more as a really, really convenient shortcut.
So here's the formal definition, and yeah, I know, it can look a little intimidating. It's kind of like a remix of the product rule, but it's got that minus sign and the extra g squared on the bottom. It is notoriously easy to mix up the order. But thankfully, calculus students for generations have used this fantastic little mnemonic to remember it. Just say it with me. Low d high minus high d low over low squared. The low is the denominator, high is the numerator, and d just means the derivative of. Trust me, it works every time. But here's a little secret for you. What if you didn't have to memorize it at all? What if I told you the quotient rule isn't really a fundamental rule, but is actually just the product rule and the chain rule working together in disguise?
The key is that you can rewrite any division as a multiplication.
So f of x over g of x is just f of x times g of x to the power of -1. And now what do we have? It's a product rule problem. And to handle that g of x to the -1 term, you just use the chain rule. So you see, the quotient rule was never a new rule at all. It's just a convenient package for the other two rules combined.
So why do we care so much about picking the right rule? I mean, really, why does this matter? Because these rules, they're the building blocks for solving much bigger, much more interesting problems. It's all about seeing the underlying structure.
So let's summarize the game plan. You see multiplication, you think product rule. You see functions nested inside each other, you think chain rule. And if you see division, you think quotient rule. Or you can just convert it into a product and chain problem. It all comes down to recognizing the pattern.
And this gets to the ultimate goal. These rules help us find the derivative, which is really just the slope at any point on a curve. So when we set that derivative to 0, we're asking a really simple question. Where is this curve completely flat? And that single step is how we find the maximum and minimum values of a function, which, by the way, is the cornerstone of optimization in pretty much all of science and engineering.
This Reddit user really gets to the heart of it. The fact that the quotient rule can be built from the product and chain rules, that is not a coincidence. It shows the deep, underlying consistency of math. It means that no matter which valid path you take, you always arrive at the same truth.
So the real takeaway here isn't just a set of rules to memorize. It's a new way of seeing functions, not as these scary formulas, but as structures to be recognized. The real question is, now that you can spot these fundamental patterns, what other connections are you going to start to see?